thank you very much for introduction. So let me share my slides. So as you mentioned, I'm in kind of entangled state between math and physics. So I was trying to address this talk for both like wider audience.
Sorry, could you make the screen larger? Is it possible that you make a full screen mode?
Sure, sure. It should be here. Okay. Is it now?
Yes, yes, perfect.
Okay. Because I also invited some colleagues of mine working in math. So I will try to address this problem for both of you, for physicists and for mathematicians. So the title is 36 Entangled Officers of Euler. And there are six of us who were working on this problem: Suhail, Radar, me, Wojtek, Bruzda, Grzegorz Reichel-Mieldziec, Arul Lakshminarayan, and Karol Życzkowski. So as you see, that there are six of us, and in fact, as already Karol mentioned, this number is kind of relevant to this talk. And if you think for a moment what is very particular in this number, the answer probably depends on who you are. But let me say that there is something particular in this number 6. So first of all, this is the smallest number, which is neither a prime number nor the power of prime, which is a bit problematic for people who got used to work with very nice structures like finite fields, among many others. So the story begins in times when some algebraic structures were not very advanced. So let me start with a very basic problem. Suppose that we have a deck of cards. In particular, we have 4 cards with 2 different suits and 2 different ranks. For instance, here we have 2 diamonds and spades and asses and kings. And we would like to arrange them into a 2 times 2 box in such a way that in each line, each column, and in each row, neither rank nor suit repeats itself. So without loss of generality, let's place the ass diamond in the top left corner. And let's think for a moment what we can place in this place, which is depicted with a dot. So it's not difficult to observe that we cannot place there neither ass nor the diamond, so the choice is very unique. It has to be a king spades. But actually the same story happened in this place of this arrangement. So we have a contradiction because we have only 1 card which is left and 2 places in which it has to fit. So such an arrangement, which is called orthogonal Latin square in dimension 2, does not exist. And let's go a bit further. So suppose that now we have 3 suits, and here I choose a choice. I choose suits, maybe not the most common. It is not the most common suit because it's a flower instead of heart or something like this. But I would like to keep the color and the suit in the same correspondence. So suppose that we have those 9 cards: ass, king, and queen, diamond, spades, and flower. And our task is the same. So let's try to arrange it into 3 times 3 matrix, 3 times 3 grid, in such a way that neither suit nor the rank of the card repeats in each row and in each column. And if I leave you for a moment, probably each of you can find such an arrangement. But let me keep going. So this is the one of possible arrangements in here. So probably you can see also cursor. Do you see it?
Well, show it again. You just start moving it. Yes, yes.
You see it?
Now, yes, we see. Mm-hmm.
Great. So you see that on the diagonal, what is repeating is the suit of the car, or a color if you wish. So on the diagonals, the colors are the same. And on the anti-diagonals, like here there are queens, here there are kings, and here there are asses. So the figures, the ranks, repeats. And in fact, this problem can be traced back to the Euler, who was investigating such an arrangement in 18th century. So it's very nice that we just repeated after Euler that such an arrangement in dimension 2 does not exist. We also found such an arrangement in dimension 3. And if you think a bit, it's not that difficult to find the arrangement in dimension 4, 5, and 6 is the problematic. 6 is the problematic number here. And also 7 is not a problem. So a bit of history on this problem. So first it was Euler who find a lot of such arrangement in many dimensions. So here I divided, I presented those numbers here are dimensions of orthogonal Latin squares. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I presented in such a grid modulo 4, not without any reason, and you will see it why in the moment. So firstly, Euler noticed that for all odd numbers, 1, 3, 5, 7, 9, 11, it's not that difficult to find this arrangement. What he also observed that for all even numbers, which are congruent to 0 modulo 4, it's very easy to find such an arrangement. And what he observed that there is no such an arrangement in dimension 2, and in dimension 6, without a formal proof, he observed that it's probably there is no such an arrangement here. So he conjectured, well, maybe this is a very small case study, but still he conjectured that there's no solution for the orthogonal Latin square in dimension D, which is congruent to 2 modulo 4. So he conjectured that there are no solution in all those dimensions here. Okay. Around 120 years after, it was formally proven that such an arrangement does not exist in dimension 6. However, it was a very exhaustive case study. Here you can see it's a grid of 8 times 8 boxes, 8 times 8 arrangement done by Gaston Tarry, who was investigating those orthogonal Latin squares, and he provided some nice case studies. And among many others, after an exhaustive search, just proving that such an arrangement in dimension 6 does not exist. It was a bit surprise in late 50s. A pair of mathematicians, Bose and Schlickhande, found that there is a solution of Euler's problem in dimension 22, and the same year also the solution in dimension 10 was found. And also with another mathematician, Parker, they proven that in all dimensions except 2 and 6, such a solution do exist. So here on the right, you can see a newspaper from late 50s. It's a New York Times, so it's not very often that mathematicians are present in the New York Times. You can read the major mathematical conjecture failed, and it's about those 3 mathematicians, which were dubbed after Euler spoilers, because they spoiled this famous Euler conjecture. So that was a bit of math. And let's now go to the quantum physics. So first of all, what is a quantum state? Quantum state is simply some element in Hilbert space. Here we work with finite dimensional Hilbert spaces. So if you are not acquainted with this notation, you can think that this is just a simply complex projective space. So apparently this setting of elements of Hilbert spaces, it's a very allows us to describe many quantum physical phenomenon, like quantum superposition, which was pushed to the limit by the Schrödinger cat's thought experiment, in which you have a cat trapped in a closed box with a small device, which with probability 1/2 release some deadly poison, and with probability 1/2 it does not. Here there's an example of such a quantum superposition where the cat is half alive and half dead, and of course it's pushed to the limit. That, as you can guess, there's some abuse in such an interpretation of quantum physics. But let me discuss briefly another phenomenon, which is very particular to quantum physics. Is a quantum entanglement. So instead of considering only a one Hilbert space, we can consider a product of two Hilbert spaces and elements of such a larger Hilbert space. So if we can go back to this Schrödinger's cat thought experiments, we may wish to describe not only a state in which there is a cat, which is depicted here, but also the state of this small device, which either liberates the poison or not. So if it's up, it means that it didn't liberate the poison. If it's down, it means that it did liberate the poisoned, and the cat is not alive anymore. So you see that there's a correlation between obvious correlation between those two states, and in some sense they are entangled. And what I mean precisely that this state on the right cannot be written as a product state of elements from each Hilbert space. So this is the definition of the entanglement. And if we want to quantify it, we can do this very easily. We can investigate the partial trace of such a state of one of the system. And we can look at the reduced density matrix, and it turns out that if it is rank 1, the state was separable, and if it is not, the state was entangled. So this is a nice way of quantifying entanglement. So if we ask what is the maximally entangled state among all states, it's very nicely, it might be nicely defined that the state is maximally entangled if such a reduced density matrix is proportional to the identity. So in other words, you may think about it that it does not contain any information about the system which was traced out. Okay, and here is the example of such a maximally entangled state in a Hilbert space of 2D-dimensional, if a product space of 2D-dimensional Hilbert spaces. So it's just a superposition over all elements like 0, 0, plus 1, 1, plus 2, 2, where all those 0, 1, 2, and 3 are some elements of the basis of each space. Okay, and such entangled states were actually used, and for instance, here there is a scheme of the famous quantum teleportation protocol, in which such a maximally entangled state might be used to teleport some quantum particle, yes, between two separate labs. Okay, but nowadays actually we are the progress is going, so we not only work with states which are a product of only two spaces, but we can work with states which are products of many smaller subsystems. So here you see there are 8 dots. Each of them is representing another subsystem, and we also would like to quantify somehow entanglement in such a larger systems. So the easiest way to do this actually is to impose the following condition. If we divide this system into any partition of 2 subsystems, for instance here, we partition this system into through this line in the middle, we would like to have the state which is maximally entangled with respect to any of such a bipartition. And in fact, such states have very a lot of interesting features. For instance, they allow us to perform such a parallel teleportation protocols and some quantum secret. They are used in some quantum secret sharing protocols. And also here, there's a nice picture how you can use those states in order to build bigger systems.
Sorry, there was some question. Could we interrupt you for a while?
Yes.
So please go ahead.
So this partitioning of system to 2 subsystems of floor of n½ should be for all possible divided?
Yes, for all possible bipartitions into systems with the same elements of states, yes? So for instance, here you have 4 and here 4, and you can divide it also like this or like that. So all possible bipartitions, exactly.
Okay, and this n½ the floor of n½ where this inequality come from?
Actually, you can easily check that for pure state, if you trace out the system which is not at least a half, if you trace at least not a half of the bigger the initial system, then you will never get identity here. So this is the lower.
Yeah. It's also a consequence of the previous part that you said maximally entangled states is proportional to identity for bipartite systems. So okay.
Exactly.
Yeah. Thanks.
Exactly. So this is the I'm sorry, I told the lower bound, but this is the upper bound, what we can actually achieve. And here there's a picture how we can use this in order to build some larger holographic codes, which exhibit some very nice properties related to anti-de Sitter conformal field theory correspondence. So and also those states interacting with combinatorics very nicely, as we can see in a moment. Okay, so let's go back to our initial problem. So let me take this 3x3 grid from the first slide, in which aces were on the diagonals, kings on the diagonals, and queens on the diagonals, and the same colors and also the suits were on the anti-diagonals. So how you can associate with such a combinatorial arrangement a quantum state? Well, indeed, you can do this. First of all, let's change each suit and rank of the card to the pair of numbers. So for instance, aces will go to the 1 on the first position. So here we have 1s on the first positions, kings to 2. Here there are 2s, there's 2 on the first position, and queens on the number 3. And let's change the suit or the color of the card also to the number. So diamond will go to the 1, spades will go to the 2, and flower will go to the 3. So we can see that on the second position in this arrangement, 3s are on the antidiagonals, 2 is also on the antidiagonal, and 1 is also on the antidiagonal. So with such an arrangement, we can easily associate a quantum state. How we do this? Simply by reading the number of row, the number of column, and 2 indices which are inside the box. So for instance, in the first row we have 1, column 1, and inside we have 1, 1. So there is a 1, 1, 1, 1, 1. In the first row we have also, and the second column we have the pair 2, 2. So it's 1, 2, 2, 2. And in the second row and the first column we have the pair 3 and 2. So in the second column and the second row and the first column we have the pair 3 and 2. And surprise, surprise, it turns out that such a state is absolutely maximally entangled with respect to the definition from the previous slide. So it maximizes entanglement for any bipartition of the system. So in fact, all orthogonal Latin squares, which I presented on the first slide, to each of such orthogonal Latin square, one can associate the relevant absolutely maximally entangled state. But the question is now, okay, and let me investigate this nice arrangement from another perspective for a moment. So we can look on this arrangement of 3 times 3 pairs of numbers in such a way that to each of such small box will be displaced by the matrix of 3 times 3 matrix, in which this pair of numbers will indicate in which small column and small row this number will be placed. So here it will be 1, 1. For the second, it will be 3, 2. So it will be 3 and 2. Here it will be 2, 3. So second small row and third small column, and so on and so far. So in fact, for such an arrangement, we associate a matrix, which is not a very random matrix because this is a permutation. And one can see that for each orthogonal Latin square, the outcome of such a procedure would be a permutation matrix. But in fact, if we look on this quantum state here, which basically is in one-to-one correspondence to this arrangement on the right, we see that this first number was indicating the big address row, and the second was indicating the big address column, while the third one was indicating the small address row, and the last one was indicating the small address column. But we can permute, of course, those subsystems. And in fact, this is the very nice property of this orthogonal Latin square, that anyway, with respect to any permutation of those subsystems, we will always end up with the matrix, which is a permutation matrix. So in fact, those three matrices which are indicated here are related by so-called reshuffling and the partial transpose operations. So let me go quickly through a partial transpose. What we are doing in the partial transpose operator, we reflect in each this small matrix the element on the other side of the diagonal. So this one will go to that element, and you can see it here. This element will be reflected here. This element will be reflected here, and so on and so forth. And the similar operation is reshuffling, so slightly more complicated. So in fact, this initial arrangement, which we called orthogonal Latin square, might be replaced by this bigger permutation matrix. So it's not 3 times 3 arrangement anymore, it's 9 times 9, with the property that those two operations, reshuffling, partial transpose and reshuffling, do not change the property that the matrix remains a permutation matrix. And in fact, this is the equivalent definition of such orthogonal Latin square arrangement. So, the question is now, of course, we know that to each orthogonal Latin square, we can associate the related quantum state, which turns out to be absolutely maximally entangled. But is it the reverse statement true? Or if it's not, I mean, we suspect that quantum world is much more subtle and much bigger than the classical one. What are the properties of absolutely maximally entangled states? And in fact, this analysis of related permutation matrices is very useful because each quantum state can be written in that form, where this Tijkl is simply a coefficient in some product state basis. So if we group those coefficients Tijkl into a pair of symbols, for instance, here I is together with K indicates the row of the matrix, and J with L the column. Here I and J are indicating the rows, and K and L's the columns of the matrix. So the state is absolutely maximally entangled if and only if those three related matrices are not permutations, but unitary matrices. And such a matrix, such a matrix U, which is unitary, but also remains unitary after this reshuffling and partial transpose operation, is called a two-unitary matrix. So we have a very nice correspondence between absolutely maximally entangled states and unitary matrices of size d square, of order d square. So let's go back to the Euler's problem. So we know that there's no orthogonal Latin square of size 2 and 6, and there are orthogonal Latin squares on any other in any other dimension except of those two. So now in quantum physics, we of course know that there is an AME state, absolutely maximally entangled state of 4 parties with the local dimension 3, 4, 5, 7, 8, and as much as you can, but maybe not in 6 and in 2. But of course, as we mentioned, the quantum world is bigger, so maybe there are some AME state in those dimensions, and they correspond to something like quantum orthogonal Latin square. I'm not going to reveal what does it mean, but actually this notion can be formalized. So in dimension 2, there's a very nice paper from 2000 by Sudbury and Higuchi that there's no quantum orthogonal Latin square, or as you wish, there is no AMA state of 4 particles with dimension 2, so 4 qubits. But still, the question of quantum orthogonality square or AMA state of 4 particles in dimension 6 remains open. And here I borrow it from the Felix Kuber webpage. You can see there's a table on the vertical axis. There's the local dimension is indicated. No, on the vertical axis, the local dimension is indicated indeed. There's 2, 3, 4, 5, 6, 7, 8. And on the horizontal axis, there's a number of particles indicated. There's 2, 3, 4, 5, 6. So we see that those absolutely maximally entangled states were found in many dimensions, although they do not exist always. And this result about by Higuchi and Sudbury, which I just mentioned, it means that there's no state which will be relevant to this place in this table. But as you see, it's very annoying that you see such a table and you see a free spot just in the middle, just on the line of your eyes. So this is the question of this quantum orthogonal Latin square of size 6. So,
sorry, white means that the answer is unknown, yes?
White means that the answer is unknown, exactly.
So green, it exists, blue does not, and white, we do not know.
Exactly. Thank you for this remark, because I looked at this table maybe too many times, so it's very obvious for me. But of course, you're right. Green, it means that state exists. This purple means it does not exist, and white color, it means it's unknown. So we've tackled this problem, and how we did it. Firstly, it's very nice always to quantify if we are going to, because we are going to look for 2 unitary matrices of size 36. So it's always nice to quantify how close to the answer we are. And it might be done by so-called entangling power. So firstly, if we have a quantum state, we can look for the linear entropy of the partial trace of the state, and by this we can define so-called entangling power. So for a given unitary gate U, we look for the average entanglement produced by this gate U, and U is here applied uniform to the uniformly distributed product states with respect to the Haar measure on the related Hilbert spaces. So it's maybe not very convenient to work with such an averaging procedure, but in fact, entangling power, this definition might be replaced, but by a more by another definition. So firstly, instead of looking for the linear entropy, we will look for the operator entanglement of the gate U, which is simply given by this formula, where lambda j are Schmidt coefficients for the matrix U. And we are going to maximize this value, as well the value of gate U times swap gate, where the swap gate simply means that we exchange two systems. So we replace this we replace this definition by the other definition. They are absolutely equivalent. So by the entangling power of the gate U, we will understand after some rescaling the operator entanglement of the matrix U plus operator entanglement U swap minus operator entanglement of the swap, which is maximal. And this is, of course, only, this is the constant value. So this entangling power takes the value from 0 to 1. And of course, we are interested in the gates which achieve this maximal value. To distinguish further between different types which are locally not distinguishable, for instance, if we plug in here the matrix U, the gate U, and U multiplied by swap, the entangling power will be the same. So we would like to distinguish those two situations. So we use also so-called gate typicality, which basically measures how different are those two values. And here there is an example from for the gates of size 4. So we have gates which are 4 times 4 unitary matrices. And you can see that there are many different families of those gates or those unitary matrices, as you wish. I'm not going to details here, but what is important is this sharp threshold here. And this sharp threshold, it means that we cannot go any further because, as you see, the maximal value of this entangling power is given by 1. So the 1 will be never achieved, and actually the maximal value of the entangling power here is 2/3. And how you can understand it? Well, there's a very nice correspondence that 2 unitary matrices achieve exactly this maximal value of entangling power. So if we know that there's no AMA state of 4 qubits, of course there is no 2 unitary matrix of order 4, which basically means that the entangling power in that dimension will never achieve the value 1. But moreover, we see that the threshold is very sharp and actually it's very far from being to 1. So let's go back let's analyze our case where we're working with dimension 6. So here there's an example of permutation matrix, 36 times 36 permutation matrix related to such a Greco-Latin square arrangement. So each of this pair of indices, it means this local address on the cell. So we can blow it to the gate of size 36 times 36. So if you compute the entangling power of such a related permutation matrix, it's pretty large. You see that it's almost...
Hello?
Yeah.
Am I audible? Sohail here. Am I audible?
Yeah, I hear you. Yes.
Yeah, actually, there's one point about gate typicality. I think it's also normalized. It should be between 0 and 1. It will be maximum for swap and half for all 2 unitary. So it is from 0 to 1.
Exactly. Thank you very much. Exactly. Yeah. It's okay. Between 0 and 1. But what I wanted to say that 2 unitary matrices are related with the gate typicality of 2 unitary matrix is exactly 1/2. So you can see that it lies on this line in the middle of this picture. Thank you very much. But going back to our case of 36 unitary matrices of order, unitary matrices of order 36, the maximal entangling power is basically equal to 1 up to the 3rd decimal place. So it's a very different situation than the one we have here in dimension 2.
One minor remark. So if we had a 2-unitary matrix of order 4, we would have a point here as those 2 lines cross somewhere here, but it's not there. It's far away, so it's easier to prove that such a point does not exist. For case d equals 6 is very different.
Exactly. And I probably have also, on the other slide, the analysis of the case for d equal to 6. So we can see the range here is absolutely different than the range in dimension 2. So the gate, which is here, it's our goal. This is our target, which we would like to find. This permutation gate, which was described on the right, is, I guess, somewhere here on this picture. And basically, we were able to find a lot of other interesting families of such a gates, which are named by some our last or surnames of people involved in this project. So here is Wojtek and Suhail and so on and so forth.
Grzegorz, G is for Grzegorz, and yes. W is for Wojciech, plus the other co-authors who were close to the right border, but not quite. Yes. Exactly.
And yeah, Grzegorz is pretty separated, but yeah. So what we used some numerical search. The following algorithm. We start with some unitary matrix U. We perform this reshuffling operation. Then we perform the partial transpose operation, and we end up with some matrix, and which is not necessarily unitary now. And we basically project it on the set of unitary matrices, for instance, by using the polar decomposition. You can easily do this. And we repeat this procedure. So if we start let me just mention that such a procedure is very effective, for instance, in dimension 3 or 4, starting from very random unitary matrix, you will end up in the 2 unitary matrix with a very high probability. And now in this, however, starting from dimension 5, it's not that easy. So there's a question from which matrix we should start with. And here there's the permutation matrix, which was on the previous slide. And if we start with this permutation matrix, which maximize the entangling power among all permutation matrices, we can go a bit farther. You see, we are farther than initially, but not that much. But if we perturb this matrix initially, so we apply some small perturbation before starting this procedure, it turns out that we can go farther on this picture, but still not to 2 unitary matrix, because our goal is to achieve 1 here. But interestingly, if we start from another permutation matrix, which in fact has smaller value of entangling power, and we perturb it, then our algorithm ends up with a numerical 2 unitary matrix with some probability. So this procedure can be repeated, and with probability, I guess 6%, it will end up in the 2 unitary matrix. So this is the plot of the convergence. So we see this is how it converges to 0, the deviation of entangling power from 1. And here there's a logarithm.
Okay.
Yes?
Yes. Are there any questions right now? Any very urgent questions? No, please continue.
Okay. So on the logarithmic plot, you really see how the convergence is going. And here there is the picture how it converges on with respect to those two measures like entangling power and gate typicality. So basically, the gate typicality is usually close to the half. Okay, so we end up with some numerical matrix, but it was numerical. So basically, it looked like this, and we were actually pretty lucky that already after applying this algorithm, in many places in this matrix were close to zero. They were numerically equal to zero. So we end up with the matrix in which in each column there are 12 non-zero elements. There are 12 non-zero elements here, here, and in third column, and in fourth, and so on and so far. So now what we would like to do is to apply some unitary, local unitary rotations. So we see we will not rotate it globally, but only locally. So with respect to the tensor product from each side, in order to find some patterns in this big matrix. And as I mentioned, we were very lucky that the structure was already partially visible because it was very natural to restrict, at least on those three subspaces, to search only on the tensor product of three unitary matrices of size 2. So what was problematic here? It was this big unitary matrix of size 6, because the search space for any kind of pattern is still big, but with a small trick we can actually eliminate it, because what we've done, we looked not for those 12 times 12 vectors, but we looked for those vectors of length 6. So each column of this matrix consists of 2 vectors of size 6. And of course, if we glue them together, those 2 vectors will be orthogonal, and there's not much to be seen between them. Not much, they are not much related. But if we split those 2 vectors into those length 6 vectors, this one, this one, this one, and this one, we can investigate some orthogonality relations between those shorter vectors. And this is what we were doing. We were searching for some nice patterns between those length 6 vectors. And with time, we got acquired with this matrix, and it started to collaborate with us in some sense. So some patterns appeared in this numerical cleaning process. So for instance, here I depicted 8 vectors, 8 length 6 vectors, which corresponds to those 4 boxes in the top left corner. And after applying some numerical procedure, we were able to orthogonalize some of those vectors. And finally, we end up with the matrix of a much nicer structure. As you can see here, there are 3 colors. Those colors are relevant to the amplitudes which appear in this matrix. There's a red, the green, and yellow. And what was very particular, that this matrix, but not only this matrix, but also the reshuffled matrix and partially transposed matrix, exhibits very nice block structure form. But the block structure was not of the one which maybe would be the most the one which would we expect here, so 6 blocks of 6 times 6, but we had 9 blocks, 1, 2, 3, 4, 5, 6, 7, 8, 9 of size 4 for each of those matrices. So let me go to the details. So in order to present this state, we'll use this tensor product form, where those indices T, I, J, K, L are coefficients in the product space as in the product basis. And basically in our solution, there are 3 non-zero phase amplitudes of elements. There's A, B, C, and interestingly, this omega here is a root of unity of order 20. So omega is root of unity of order 20, and each of those amplitudes might be expressed in terms of this root of unity. So here is the solution. So you see that there are 9 blocks, and ij, all non-vanishing coefficients are placed in this table. Ij is indicated in row, as this pair here, and KL is indicated in column. So green is related to the amplitude A, yellow with B, and C with red color. So what is very funny that there are 2 very nice patterns in this, maybe not patterns, but there are two very nice particular phenomena which we can observe in this matrix. So firstly, this A, B, and C are related via Pythagoras theorem. And yeah, but what is maybe less expected is that B divided by C is basically given by a golden ratio.
I'm sorry, B divided by A, I presume.
Yes, you're right. You're right. B divided by C would be
something different.
Something different. It will be not a golden ratio. So B divided by A should be here. And in fact, this is not that much surprising if we remember that A and B are presentable in forms of roots of order 20, because we can, as we can see, there is a unit circle here, and those dots are related to the roots of order 20, and we can see that this omega plus omega bar has length of a diagonal of the pentagon, while this omega to the 3rd power plus omega bar to the 3rd power is basically the length of the side of the pentagon. So this is where the golden ratio comes from, but what is actually behind it is this root by this order of the root. So going back to just the last slide, so going back to the problem of officers of Euler, how we can present them. Of course, the traditional French deck of cards is not enough, so we have to introduce some additional colors, suits. So here there's a sailing rudder and also a tennis racket. This is some suit which was introduced by other people. And we would like to fill the 6x6 grid not with 1 card in each box, but in a superposition of 2 cards or 4 cards, as it is indicated here. So of course, this is not an orthogonal Latin square, but this is quantum orthogonal Latin square, in which we forget for the moment about the related phases. And let me just finish with another interesting grid, that if we applied some coarse graining procedure, for instance, each ass and king will be replaced by letter A, and queen and jack by B, and 10th and 9 by C, and spade and club by alpha, a diamond and heart by beta, flower and star by gamma, we can present this solution in form of coarse-grained orthogonal Latin square, in which each pair of symbols, here is alpha and A, appear exactly 4 times. It's here also, and it's also here, and it's also here. Moreover, on each position, in each row, each symbol appear twice. There's alpha here, and there's A here and here, while alpha is here and here. And the same holds with the column. And those 3 features basically stems from the nice property that the matrix we obtained have very nice, have this block structure of 9 4 times 4 blocks. Okay, I think that I will finish here, and I will be happy to answer all questions which anyone has. Thank you very much.
Thank you very much. Let us then thank the speaker again and open the discussion. Who would like to ask the first question? Please, you are encouraged to ask.
Okay, I have a question.
Yes, Masoud, please.
Thanks for the talk. It was super interesting. Could you go to the slide that you show that mathematician solves some numbers for this orthogonal Latin?
Sure. So it was from at the very beginning, yes?
Yeah. That you show that it's gonna be a modular of 4.
Ah, yes. It should be somewhere here. The presentation is pretty heavy. There are a lot of pictures, so it's here.
Yes, exactly. Yeah. So we saw that there is no orthogonal Latin score for number 2 and 6.
Exactly. Mm-hmm.
So why don't we change this modular to something else, to have another number of particles? I believe that we can solve some extra problem in finding there is, for example, no absolutely maximally entangled states for, let's say, 5 particles or 6 particles with different dimensions if we change the modular.
Yes. So here I absolutely agree.
Yeah, because here there is no pattern after 6. So for 10 we have this Latin score. But if we change the modular, that 2 and 6 gonna be in this first column, for example, to modular 8. So we have 8 particles, and then we can talk about AM states for 8 particles with different dimensions.
Mm-hmm. So on this picture, only the local dimension is depicted. The number of particles is, let's say, 4 always.
Yeah, but we can change for a number of particles, for example, 8, and still we have something similar to this table.
Absolutely, and this question is open as far as I remember. For AME state of 8 particles with local dimension 6, I guess it's still open.
Mm-hmm.
So yes, we can do this, but actually, what is the question?
Just wanted to know if it's possible. This was the question, if it's possible.
So the search space is, of course, much larger, which is problematic. And if you go to this algorithm that we used, oh, maybe here, if you have 8 particles, it will be not enough to consider only those 2 operations, reshuffling and partial transpose. You will basically have 8 choose 2 different bipartitions. So you will have 8 choose 2 different operations on this big matrix, which should end up still in the unitary matrix. So the procedure will be very long, I guess. It's possible to do this, but I'm not sure whether you will get a result.
Mm-hmm. Okay.
So the difference is here, you have to consider more and more operations if you increase the number of particles.
If I may add a comment.
Yes, please, please.
So basically, it is only restricted to the case of 4 particles that there is this correspondence between orthogonal Latin squares and quantum AMA. And it is only a coincidence that there is this modulo 4. I mean, this does not have, as far as we know, direct connection to the case that there are 4 particles. This is also connected to a fact that if you have 4 particles, then the whole state can be grouped into a unitary matrix. If it is of other dimensions, then there is no such simple connection. And well, then as far as we know, it is not possible to extend our setup to another number of particles. So to sum up, it's only a coincidence that there is this modulo.
Thank you very much, Grzegorz. The only minor remark, if you consider 6 parties, you can consider orthogonal Latin cubes, and for 8 particles, hypercubes, but of course, much more difficult. Fine. Any other questions?
Yes, can I ask something?
Yes, yes. Hello, Barbara.
Thanks a lot for the talk. So it's the first question, actually, well, I asked the second question first because it's related to the one that you discussed right now.
Mm-hmm.
I mean, of course, one thing is to do systematically search for the solution or to prove that it doesn't exist.
Mm-hmm.
But another thing is once you have a solution, of course, you can use it to see whether it also provides you a solution for a different dimension, right? So from this point of view, I guess it would be worth trying.
Yes, absolutely. And if you tackled this sort of question, let me just go to the very last slide, because it was very exhaustive to do this numerical cleaning, for instance, and also other things. But actually on the last slide, we end up with the relatively simple picture of this coarse-grained orthogonal Latin square. And this picture corresponds to the fact that we have very nice structure, a block structure on the unitary matrix, and also reshuffled matrix and partially transposed matrix. So we can actually do other way around, starting from such a coarse-grained Latin square, for instance, find by this block structure of matrix, which is preserved under the reshuffling and partial transpose, and then try to arrange those indices in this smaller block structured matrix already.
Mm-hmm. Exactly. Well, I mean, this part, but I guess that the answer would take a bit too long, because I mean, why the fact that if you do this coarse graining, that this leads to the simplified lattice. Why this is equivalent or reflecting the fact that you can find the block structure is not clear to me. Is it obvious or?
It's not obvious, but it might be shown that it is.
Yeah.
It might be shown that basically, if you have this structure, so the fact that each pair of symbols repeats 4 times, it reflects the structure of the initial matrix. And there's some nice property, for instance, if you consider this first top left blocks, you see that alpha is coming here, beta is coming here, and A is coming here, and C is coming here. So we see that those 4 indices, A, C, beta, and alpha, are grouped together in a block. And the same repeats also here, and in all those blocks, which reflects to the block structure of the reshuffled matrix. And the same is, for instance, if you consider this, this block here, this block here, this block here, and that block here. So alphas, gammas, C, and A also form this 4 cyclic, let's say, property. So that would reflect the structure of the reshuffle of the partial transpose matrix.
Okay, thanks.
So
Can
may
I
I
ask
add-
another question?
Yes, Barbara, please.
So can you go back, because you showed us now the table for the entries of the coefficients of your state, but I'm sure that you also tried to somehow understand what the state is, no? So do you have somehow an expression of the state in terms of, I don't know, two parties versus 2 parties and the states in some basis? Or because it seems that there is some structure if you write this in a kind of an entangled basis, maybe of pairs or something like that, or?
We're trying, but the problem with this matrix is our phases. You see, we have those roots of order 20, and even though up to some multiplication by the diagonals matrix from the top and the right, though all those matrices are basically very simple, they are the same. Among local operations, it's very difficult to adjust those phases, and they are really we don't have a full control over them.
Yeah, this will not be local, right? Cannot be, because otherwise you can.
Yes, so yeah, exactly.
No, but can you write it as like a global phase gate applied to some simple state or something like that?
You can write it, yes, definitely. You can write it as a global phase gate from both sides, and the permutation gate, for instance, from both sides, and you will basically have this structure in which all blocks are the same, except of the in the middle. So yes. Yes.
So if somebody would ask you, give me a simple description of the state, what would you give them?
I think I would give this.
Simple. Okay, good. Okay, thanks. Thanks a lot for the talk and also for the invitation. It was very interesting.
Thank you. Thank you very much.
Are there any further questions or remarks?
Can I add one remark?
Yes.
So Adam, if you can go back to this coarse graining, because
probably move forward.
Forward, yeah, basically forward.
Okay.
So how to see this, as to the previous question, how to see this coarse graining. So in here, you have this and this one, this thing, which is the same. And you can see that this would correspond to these two. So basically, this coarse grained structure comes down from the fact that you have these aces and kings, and whether they are from black or red or blue color. So this basically coarse graining can be read from this card structure. So this is the simplest way I think you can put it forward.
Mm-hmm.
Yes, thank you. Are there further questions or remarks?
Yes, I
Yes.
have a question.
Yes.
Okay. I have a number of questions, but I just limit myself to one. Well, we know that for orthogonal Latin square, if you have two Latin squares, so you can get orthogonal Latin square. We know that this is not a fact for quantum orthogonal Latin square. So it's not constructed by two quantum Latin squares.
Sure.
And now that you have this quantum orthogonal Latin square for this size of matrix, I think that construct MA for 6. So what if you use this one quantum orthogonal array and one quantum orthogonal Latin square, and you mix it with another quantum orthogonal Latin square? Can you construct MA8 6? Maybe I explain it a bit bad, but you see what I mean. You have two quantum orthogonal Latin square and you mix them like what we had in a classical scenario, and then you construct a bigger quantum Latin square sort of by mixing classic and quantum. Do you think you can construct MA8 6, or it's very obvious that it's not?
I guess no. You know the best. You are probably the best person to know it, that this kind of mixing, of course, it cannot be simply just a tensor product. It's pretty tricky how to really do this. So I would be very surprised that you can apply this kind of mixing procedure with respect to this sort of matrix. I would rather look for another combinatorial object, not orthogonal and not coarse-grained Latin square, but by some cube with some properties, and then try to fill those indices in the blocks.
No. What I mean is that you have this quantum orthogonal Latin square, you get another quantum orthogonal Latin square with the same structure, and then you go to hypercube. So you, but using classical scenario, so you construct, I don't know, classical plus quantum orthogonal Latin hypercube in this case, in this part, and then with that, then you will have larger hypercube, and then these two columns are coming from the, how to say, setting these particles, and then you can construct MA8 6. Or you need to just go from the beginning.
Perhaps we can. We have to try. We were not trying so far.
Let me answer in a very.
But this is very tricky because you are combining classic and quantum. So
I think that arranging of such an arrangement, big arrangement, is very tricky. Okay. So yeah.
Okay, we should finish soon. But are there any other urgent questions?
I have a question.
Yes, Dado.
Yes. Well, first of all, congratulations to you, Adam, and all the team for this very nice solution. So I'm happy to see that this the beginning point is the multi-unitary matrices, which is a concept that we introduced in 2015 when I was in Krakow. So, well, my first question is, could you please go to the algorithm?
Sure.
So if I remember correctly, the correct seed is a classical quasi-orthogonal Latin square, which is the second one appearing there. So this successful seed is taken from the literature, or is your guess?
I think it's not me who should answer this question. It was not me who was looking for the seed. It's probably Suhail, yes?
Yeah. Actually, it was it was not in the literature. So we actually were playing with different seeds and all that. As is mentioned there, I mean, if you start with the sort of best permutation, the best you can do in terms of entangling power is 0.999, and then we actually tuned our seed to this PS tilde, and it actually leads to this 2 unitary of order 36. And it turns out this is not the only seed permutation or only structure which can give. There is actually many more seed permutations which can actually lead to a two-unitary matrix. The reason for choosing this one, it turns out that in this case, the final two-unitary matrix is actually in this nice block form. Sometimes if we take some other seed unitary matrix, which is quite far away from the edge, it's full and it's not nice to, I mean, this numerical cleaning, so to speak, is sort of difficult in those cases. But it turns out that there are other seed permutations also which can be used to, I mean, to get the two unitary also.
Can I just add something briefly?
Yes.
Arul here.
Yes,
Hi,
please.
Dardo, hi. Thanks for the question. And Sohail, isn't the starting point not just the permutation, but it actually
it's neighborhood of that. It's neighborhood of that.
Yeah, and
I think this
actually,
is important. So we don't start exactly from permutations, but very, very close to it. And one remark concerning science. At the beginning, the algorithm goes backwards. We want to go in this direction. So basically it means if you start doing something and you go first few steps in the wrong direction, don't give up. Maybe the procedure will turn around and will go exactly to the aim. So I think it's a very nice example. You should not give up too
this is the
quickly.
very first step only here, which is going backwards.
But still, so you cannot give up. The first step does not work.
Yeah. No, actually, I just want to also add that, you know, the best permutation does not lead there because there's a very strong attractor nearby, which is this P, which is this other matrix, which is close to that. So it's a rather complex landscape with a lot of attractors under this algorithm. And maybe this one being at the center of the, you know, around GT is half already was helpful, but we are still not clear actually what is the optimal kind of permutation or neighborhoods of permutations or seeds. There are other seeds which are not permutation, which can also lead to two unitary. So yeah, thanks.
Great.
Thank you very much. So the last question, yes?
Yes, and I have another question. So now that this problem is solved, my question is, what is the lowest dimensional case that remains open?
Maybe Felix knows the answer.
I think it's 8, yes? It's 8 particles and 4 quarks. Yes?
In this table of Felix, the 7.6 it is in white, but perhaps this is already known. And 8.4 is also mentioned there in white, but I'm not sure if this table is updated or not. Felix?
I think it is. I think that 8.4 is still open. And 8.6 as well.
So for 7 parties, 7.6 is the lowest, and for 8 parties, 8.4.
I think so.
I have Felix table right in front of me, and I see I'm at 7.6. But okay.
Yeah, so I think that's starting from 8. 7 is always close.
So there was a message from Felix that he will update the table. Very nice. And Felix, could you then tell us which is, from your perspective, the next aim, the next target? Okay, if this is not the case, I think we should thank Adam for a very nice talk. And thank you for coming to Krakow from such a long distance. We are very pleased to have so many people in the audience. Thanks for your visit. And well, see you again. Adam, thank you very much.
Thank you. Thank you very much.
Thank you, and bye-bye. Thanks. Thanks, Paolo. Yes, thanks all the people from the audience, especially those who came very long way, especially Dardo from South America. And also, wow. Great.
Thank you, Adam.
Thanks, Zahra. Yes, you came from US now. Yes.
Yes.
Yes, yes. Thank you. Thank you very much. Bye-bye.
See you all tomorrow.
Yes, yes.
Bye.
Bye-bye.